is that potential is equal to I into R, current into resistance. So today's chapter is magnetic effect of electric current, right?
Yes, sir.
So let me just introduce these things that we have already learned. That in the previous chapter, in the previous chapter on electricity, we learned about the heating effect of electric current. What was the formula for heating? Did you remember?
I square RT.
Yes, correct. So, what could be the other effects of electric current, right? That is our main question. What could be
Yes.
the other effects of electric current? What else there can be? So, we know that an electric current carrying wire behaves like a magnet, right?
Yes, sir.
We know that uh, copper wire carrying electric current behaves as a magnet. Okay, what happened? Sorry, there was one scientist. Okay, he was doing some experiments. So there was one compass needle near to the electric wire, right?
Yes, sir.
So what happened when the electric current passes through through this wire? The electric needle was deflected. Okay, its second position was somewhat like this. Okay, so the scientists observed that whenever whenever we pass electric current through the wire, magnetic needle deflects. Okay, so that is how on this experiment we know that electric current carrying wire produces magnetic field, or we can say it behaves like a magnet.
Yes, sir.
Understood?
Yes.
So first of all, write this down. I'm giving you a 5 minute. Okay, then we'll move on. Is it visible?
Yes, sir.
Okay.
Yes, sir.
Okay. So basically we see that the needle is deflected, right? Suppose this was its initial position, and after, when current passes through the wire, it okay, let's suppose this is the initial position. Okay, there is no current in our copper wire. When uh, charge of electric current, sorry, flow of charges takes place in the wire, the magnetic needle deflects, okay, at some angle, right?
Yes, sir.
Let's say it's theta, okay. So why this happens? It is basically, the reason behind this deflection is because the the electric current carrying wire behaves like a magnet. Okay, this is because of the magnetic effect of the electric current, which is passing through the electric wire, right?
Yes, sir.
So it means that the electric current through the copper wire has produced a magnetic effect, right? Basically,
Yes, sir.
magnetic effect. So let me change the color. So thus we can say that electricity and magnetism are linked to each other, right?
Yes, sir.
Thus we can say that electricity and magnetism are both linked to each other, right? So then what about the reverse possibility of an electric effect of moving charges? Oh, sorry, moving magnet. What about the reverse possibility of moving magnet, of moving magnet? Here we can see the charges were flowing through the wire, right? Basically, electric current was flowing through the wire, and because of this electric current, magnetic needle deflects, or we can say it produces magnetic field, right? It produces some magnetic effect, right?
Yes, sir.
So what about, let's say there is an electric wire, okay, and you move a magnetic or we can say a magnet. This is our magnet, let's say. This is our wire. What if you move this wire back and forth around this wire? Then what will happen? It can we suppose that it will create electricity in this wire, or we can say it will produce electric current in this wire? Huh?
Yes, sir.
This is the reverse possibility, right? If
Yes, sir.
electric current can produce magnetic effect, then why not moving a magnet around the wire can produce an electricity, or you can say electric current? That must also be possible, right? It has to be. Are you getting my point?
Yes, sir.
So that is also possible. Okay, that we are going to discuss below. Okay, let us just first just write all this down. Okay, then I'll discuss further. Till now, any doubt, any question?
No, sir.
Okay,
No,
write this
sir.
down.
Yes.
So, in this chapter, we will study magnetic field. What are the electromagnets? What are the effects of magnetic field, etc., etc. Okay,
Yes, sir.
electric generator, etc. I'm not mentioning all these points. Okay. So next, our topic, or you can say subtopic, is magnetic field and field lines. So let's just first talk about the magnet. Have you ever seen a bar magnet?
Yes, sir.
This is called a bar magnet. There are two poles, right?
Yes, sir.
North pole and south pole. Okay. So these are two poles, North pole and South pole. Just like electricity, okay, there were charges, right?
Yes,
Positive
sir.
and negative. Likewise, here there are two poles, south and north. We have seen that positive charges repel each other, right?
Yes, sir.
And positive negative charge, or we can say unlike charges attract each other. Likewise, like poles repel each other, and unlike poles, what do they do? Attract each other. Okay,
Yes, sir.
like poles repel each other, and unlike poles, attract each other. That's why if you bring two bar magnet nearer to each other, okay, and if this is north pole and this is south pole, then they will attract each other and eventually they will stick to each other, right? That is what
Yes, sir.
happens. And sorry, this is our south pole and this is our north pole, and it behaves like a one huge magnet, having north pole this side and south pole this side, right?
Yes, sir.
Okay, write this down and we'll move further.
Yes, sir.
Done.
Yes.
Now we all have observed that at some point, right? That if you place a piece of iron, right, nearer to the magnet, what it does, it attracts the iron piece and it sticks to the bar magnet, right? That is what happens, right?
Yes, sir.
So why this happens? If you put the iron piece far away from the magnet, it will not attract the iron piece, right? But if you place it nearer or at some distance, it will attract the iron piece and it will stick to the bar magnet, right? So, what is the reason behind this behavior? Okay, basically, what is this? So, that's why we are going to do a simple experiment, okay, and we'll discuss what actually is going on in this phenomena, okay, in this experiment.
Yes, sir.
So, what you need to do is there is an activity, or we can say an experiment. First step is fix a sheet of white paper on a drawing board using some adhesive material. Second step is place a bar magnet in the center of it. Sprinkle some iron fillings uniformly around the bar magnet. Okay? Now tap the board gently. Okay? This is the famous experiment. Okay? And from this experiment, we get an idea of magnetic field, or we can say magnetic field lines, right? So, by doing this experiment, if you put it gently, okay, and sprinkle some iron fillings, by tapping it, you can see the iron fillings arrange themselves in this manner, right?
Yes, sir.
Let's say this is our north pole, this is our south. So what are these lines? Okay, these lines are called magnetic field lines. And this region around the magnet is called uh, field of field of the magnet, which is our magnetic field, right? Are you getting my point?
Yes, sir.
Okay, so what happens? The iron fillings arrange themselves in a pattern, as you can see in this figure, right? So what does this pattern demonstrate, right? That is the question. What does this pattern demonstrate? So the magnet exerts its influence in the region surrounding it, right? This is the region where the magnetic field lines are, right? Therefore, the iron filings experiences a force. The force surrounding a magnet, right? First of all, write all this down and we'll discuss further.
Yes, sir.
Okay. So simply, so what right now I'm writing a definition, okay, which is not in your NCRT textbook. So please note this. This is very important definition. The region around a bar magnet when putting iron piece. What is the spelling of piece?
PIEC.
Or magnet? It experiences the force is called magnetic field. Understood? The region around
Yes.
which a bar magnet, when putting the iron piece for a magnet, it experiences a force is called magnetic field. So it is having a magnetic field around itself, right? That's why
Yes,
by
sir.
putting any iron piece or any magnet, it attracts it towards its pole, right? Whether it is south pole or north pole. So they are called the magnetic field lines. These are the magnetic field lines and the region is called magnetic field. Okay. We generally denote magnetic field with the symbol B. Okay. So remember this definition. Okay. This will be very helpful because this definition is not given in your textbook. Okay.
Yes, sir.
So write this down and we'll move forward.
Yes, Photon.
Okay, so now let's just talk about magnetic field. So magnetic field has both magnetic field has both direction and magnitude. Why? Why it has magnitude and direction both? Ishan.
So it goes from north to south, so it has the direction of positive to negative.
Because magnetic field is a vector quantity. Okay. We are going to talk about poles and all this, but remember magnetic field is a vector quantity. So now what is the direction of magnetic field? So direction of magnetic, we usually take that magnetic field lines emerge from the north pole and it enters in the south pole, right?
Yes, sir.
So that is the direction of magnetic field. Therefore, it is taken by convention that the field lines emerge from north pole and what merge at the south pole, right? But
Yes, sir.
what about the inside? Inside its direction is completely reverse. It is south to north, right?
Yes, sir.
So let's just write this all down that we have just discussed. Okay. The magnetic field has both direction and magnitude. Magnetic field is a vector quantity. The direction of the magnetic field is taken to be direction of magnetic field is taken to be north to south pole. Okay.
Yes, sir.
It emerges from north pole and merges at south pole. But inside the bar magnet its direction is reversed. It is south pole to north pole. Okay, so
Yes,
write
sir.
this all down and we'll move further.
Yes, sir.
Okay, now let's talk about the relative strength of magnetic field. So as you can see, nearer to the north pole, magnetic field lines are dense, right? Nearer to any pole. As you can see, as you move away from the poles, magnetic field lines gets distributed, right? But uh, at the poles, the field lines are denser, right? Hello.
Yes, sir.
So that
Yes, sir.
means here magnetic field strength is stronger. Okay, at both the poles. As you move away from the pole, the lines gets distributed, and its intensity, or we can say its strength, decreases as you move away from the poles. Okay, and one thing you need
Yes,
to remember is that magnetic field lines can never cross path, right? Like let's take this bar magnet. If two lines are crossing each other like this way, they are crossing here, right? Hello.
yes, sir.
So this
Yes, sir.
is not possible. Okay, magnetic field lines cannot cross path. If they cross the path, that means here the magnetic field line, the direction of magnetic field line in this direction. Okay, and for here and here its direction is this, right? So at this point, it is having two directions. Now remember, a vector a vector cannot have two direction. Okay, it will
Yes, sir.
only have a one direction. So that means magnetic field lines cannot have two direction. That means they cannot cross each other. Okay, so magnetic field lines cannot cross each other. They never cross each other. So please do keep this point in your mind. Okay, that magnetic field lines cannot cross each other, or we can say they do not intersect each other. So let me just write it in the words that the relative strength of the magnetic field is shown by the degree of closeness closeness of the field lines. Okay, denser the lines, stronger the magnetic field. Okay,
Yes, sir.
so just a second. So the field is stronger at the poles. Field is stronger near the pole, near the poles. Okay,
Yes, sir.
now this is the most important point. Okay, no two field lines are found to cross each other. If they did, it would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. Okay, if you place here a compass needle, it will show two direction. Now you and me and all of us know that compass needle only shows one direction, right? It is having north and south pole, so it will at a time it will show only one direction. It cannot show this and this direction simultaneously, right?
Yes, sir.
So that's why if the magnetic field crosses each other, that means they are not magnetic field lines. Okay, magnetic field lines never cross each other. If they do, that means at the point of intersection there are two directions, which is not possible. Okay, any
Yes, sir.
question? Any? Huh?
No, sir. No question. No
Okay,
question.
write this down and do let me know. Sorry.
Yes, sir.
Now let's just talk about magnetic field due to a current through a straight conductor. Magnetic field due to a current through a straight conductor. Okay,
Yes, sir.
so the experiment is simple. What you need to do is take a whiteboard, okay? Make one hole and pass a wire through it, okay? And connect it to the battery. Now sprinkle some iron fillings, okay? First of all, place a magnetic needle on top of the whiteboard. This is our magnetic needle. Now, this is, let's say, this is our key, okay? Now, sprinkle some iron fillings, okay? Now, when you switch on the key, what happens? Current will flow from current flows from positive to negative or negative to positive. Ishan, what is the direction of
Uh,
electric current?
Positive to negative.
Okay, so it will start flowing to the wire, okay? And we all know that it produces magnetic field, right?
Yes,
So these magnetic field, sorry, these iron fillings will be arranged in this manner, okay? In a concentric circles. They will arrange themselves in a concentric circles, okay?
yes, sir.
So from here we can see that the magnetic field produced by the electric wire is different from the bar magnet, because bar magnets, the magnetic field lines of bar magnet were like somewhat like this, okay? But
Yes,
here we can see it is making circles, right? So here, on passing the electric current, we can see that the iron fillings arrange themselves in a concentric circles. So here, from here we can say that here the magnetic field lines are concentric circles, right? They are different from the bar magnet, but still they are magnetic field lines. Now do one thing, increase the electric current. What will happen? So first of all, by passing the electric current, you can also observe the deflection in the magnetic needle, right? It will deflect. Suppose the initial position was this, and after passing the electric current, we can see that magnetic field, magnetic needle is now in this direction. Okay, are you following this?
yes, sir. Yes, sir. Yes, sir.
Okay, so we can see that it deflects at some angle, right? Now do one thing, increase the electric current. What will happen? Okay, magnetic needle will deflect more, right?
Mm.
Okay,
Awesome.
now decrease the magnet. If you decrease the electric current, then magnetic, let's suppose this is our initial position. By decreasing electric current, it will deflect not much, okay? So we can say a poor electric current contributes, it will not deflect much of a magnetic needle, right? Now if you place further your magnetic needle, it will also not show much of a deflection, okay? That's the obvious reason, because if you take a magnetic needle away from the wire, magnetic field lines, we also see that magnetic field lines are denser, nearer to the wire. Okay, and
Yes,
as
sir.
you move away from the wire, they separates themselves. Okay, so that means at far further point they are not that much stronger, but nearer to the electric wire it is much stronger, right? Magnetic field is much stronger. So this is the experiment. Are you getting this all this stuff?
Yes, sir. Yes, sir.
Okay, so let's just write all these things in words. Okay, so that's it. That's what the experiment was. Okay, magnetic field due to a electric current through sorry, due to a current through a straight conductor. So from here we concluded that the magnetic field lines here are circular ones. Okay, they are making concentric circles. Here we also see that if you increase the if you increase the electric current, magnetic field increases. If you decrease the electric current, magnetic field decreases. Okay, so let's just write all these points. Okay, and some questions also. So what happens to the deflection of the compass needle placed at the given point if the current in the copper wire is changed? If current changes, what happens to the needle? Okay, I'm sure you can. Sorry about the handwriting. So we have performed this experiment, right? So if the current increases, the deflection also increases.
Yes, sir.
Deflection also increases, right? It indicates that the magnitude of the magnetic field producing at a given point increases as the electric current through the wire increases, right? So what happens to the deflection of the needle if the compass is moved from the copper wire but the current through the wire remains the same? That means if current remains same but you move compass away from the wire, obviously what happens? Deflection decreases, right or wrong?
Yes. Yes, sir.
So as the distance increases, deflection decreases. Okay,
Yes, sir.
also it can be noticed that the concentric circles representing the magnetic field around a current carrying wire became larger and larger as we move away from it. Okay, so write all these points down. Okay,
Yes.
any question?
No, sir. Yes, sir.
Also, not to forget, if this is our wire, current carrying wire, suppose the initial direction of electric current was in upward direction. Okay, so you will see magnetic field lines around it. Okay, and the direction of magnetic field lines will be in this direction. Okay, this is the
Yes, sir.
direction, initial direction. Now, what if you change the direction of electric current? What do you think? What will happen? Hmm?
Changing, then the electric current will reverse, right?
No, no, we
Change
have
its.
reversed the direction of electric current.
Yes, sir. The concentric circles,
Hmm.
magnetic uh, effect.
They are magnetic field lines. Okay, so
Yes.
initial direction of magnetic field lines was in this direction. When the current was in the upward direction. Now the current is in downward direction, then the magnetic field lines direction will be in opposite direction, obviously. Are you getting my point? Have you facing any problem understanding this concept? Please do let me know. Okay.
No, sir. No problem.
Okay. So is this the anti-clockwise or clockwise direction? First one.
Anti-clock.
This is
No,
the
clockwise. Clockwise direction.
okay. From saying let's suppose we are saying from here. Okay. Top view. If we draw the top view, it will somewhat look like this way.
So the first is anti-clockwise and second is clockwise.
So first one is anti-clockwise. And if you see this from the let's draw the top view. Okay, so top view will somewhat look like this. So this is clockwise, right?
Yes, sir.
So please remember this. If the current is in upward direction, the direction of magnetic field lines will be anti-clockwise, right? And if the current is in downward direction, its direction will be okay. I will ask you this question after 2 to 3 lecture. Okay, so please do remember. And question comes from these concepts. Okay, they are the core concept of this chapter, which is magnetic effect of electric current. Okay, and this you will face this in your upper higher standards also, because there is one chapter in 12th which is magnetic effect of moving charges and magnetism. Okay, there you will learn all this stuff again. Okay, and you are going to solve some JE questions also. Are you getting my point? Are you uh, getting the seriousness of this concept?
Yes, sir.
Okay, then draw this and please do let me know if you done it.